Okay, today we're going to learn lesson 5 of unit 4, characteristics of functions, which is inequalities of combined functions. So first, let's have a look at today's learning goals. After this lesson, you are expected to understand that a variety of real-world problems can be modeled using the combined functions. And you should also be able to develop a model to solve real-world problems that involve combined functions. Okay, so we'll use 2 example questions to illustrate these concepts. First, let's consider the first example question here, which is to combine musical notes. So here you are given a list of the common musical notes with their frequency. And the background information is given by these 2 paragraphs. The graph of the pure note can be modeled by the function it equals sine 2 pi ft, where f is a frequency and I is sound intensity. T is the time in seconds. According to the music theory, notes sound good together when they cause constructive interference at regular intervals of time. So these are the questions you're going to solve. First, graph the intensity functions for C and high C. Then graph the combined function for these 2 notes struck together. Describe the resultant waveform. And question B, a C major triad is formed by striking the following notes simultaneously. C, G, E, which is Do, Mi, So. Graph the combined function for these notes struck together. Explain why these notes sound good together. The next question is graph the intensity functions for C and F sharp and the combined function for these 2 notes struck together. Explain why these notes are discordant, which means do not sound good together. Okay, so I'll give you 15 minutes to solve these questions. Okay, and then after that we'll have a look at the solutions together. Okay, you can start now. Note here, probably you'll need some technology such as like calculator or the online tools I just showed you previously. Okay, you can start now. Okay, now let's have a look at the solutions of this question. First of all, we can determine the waveform for C and high C by substituting their frequencies into the intensity function, right? So IC in terms of T equals sine 2 pi times 262T, right? Because C is here. And this can be simplified to sine 524 pi T. And I high C in terms of T is sine 2 pi times 524T, which is sine 1048 pi T, right? And then we can use technology to graph these two functions respectively. So let's do this using Wolfram Alpha, the online tool. First, we want to plot sine 2 pi times 524. Sorry, there is no 2. This is 524T, right? 524 pi T. 524 times pi times T. So let's have a look at the graph here. This is sine 524 pi T. And we also want to plot the other function, which is sine 1048 pi T, which is also a sine function, right? Okay, now let's plot the combined function. Okay, the combined function is simply add these two functions together, which we have first sine 524 times pi times T. And next we have sine 1048 times pi times T. So let's have a look at the combined function. Okay, so as you can see here, this is a graph of the combined function. If you zoom out, you can see that there is a clear pattern of the combined function, right? And so we can make the conclusion, this waveform is periodic. According to the graph, you can see that the new form is periodic, right? It is basically sinusoidal with a slight variation at regular intervals. These notes will sound good together, okay? Because according to the music theory, notes sound good together when they cause constructive interference at regular intervals of time. Okay, so this is question A. And using the similar method, we can also plot the combined function in question B, which is sine 524 pi T plus sine 660 pi T plus sine 784 pi T. Okay, so let's have a look at the combined function. So this time we have 524 pi T plus sine 660 times pi times T, and then plus sine 784 times pi times t. So let's have a look at the graph of the combined function. Okay, so this is a graph of the combined function. So let's put it in our lecture slides. This function will look like this. And as you can see here, this waveform is considerably more complicated than a simple sinusoidal waveform. Note, however, that there is still a regular repeating pattern. So as you can see here, this is also a roughly periodic function, right? There is still a regular repeating pattern to the form, which suggests that these notes will also sound good together. The multiple variations along the cycle actually gives a chord its interesting character. Okay, next, we consider the combination of C and F sharp. Again, use similar method. We can plot the combined function using the online tool. So let's have a look at the combined function. Combined function is sine plus another sine. First is sine 524 times pi times t, right? And second function is sine 740 times pi times t. So let's have a look at the combined function. So here is the combined function. Let's put it in our lecture slides. And from the graph, we can see that the crest and trough of these two notes do not coincide at regular intervals. There is no apparent pattern, right? So that suggests that these two notes will not sound good together. This waveform does not appear to be periodic, confirming that C and F sharp are discordant notes, which means they do not sound good together. Okay, so please have a look at the question here. Let me know if you have any questions to ask. All right, if no questions, let's have a look at another example question. Pass of a skier. A skier is skiing down a 100-meter hill at a constant speed of 1 meters per second through a series of moguls or small hills. The constant slope of the hill is -1. Assuming that moguls measure 1.5 meters from crest to trough and are roughly 5 meters apart, develop an algebraic and graphical model of the height of the skier versus time. Okay, again, I'll give you 15 minutes to think about this problem first, and then we'll have a look at the solutions together. Okay, you can start now. All right, let's have a look at the solutions to this problem. So note here we can break the desired function into two parts, right? First, determine the function for the skier's height, assuming that there are no moguls. Then add the effect of the moguls. So if we neglecting the effect of the moguls, the path of the skier as a function of height versus time can be modeled by a straight line, right? So note here the rate of change of height versus time is minus 1 meters per second, right? And the hill is 100 meters high. That means the straight line can be given by the function ht equals minus t plus 100, right? When t is 0, h0 is 100, meaning that the skier is at the top of the hill, right? And when t is 100, h100 is 0. That means when 100 seconds passed, the skier should be at the bottom of the hill, which means the height is 0, right? So if we do not consider the effect of the moguls, the skier's path in terms of height versus time can be given by this line. Of course, t is greater than or equal to 0. So we need only to keep this section here between 0 and 100. T should be equal to or greater than 0 and less than or equal to 100, right? Okay, next let's consider the effect of the moguls. To model the skier's height through the moguls, ignoring the slope of the hill for the moment, generate a sinusoidal function to reflect the correct amplitude and wavelength. So note here the crest to trough distance of the moguls is 1.5 meters, right? This is given information, and they are 5 meters apart. So we can draw a sketch of the desired function here, and the amplitude A is actually half the crest to trough distance, right? So the amplitude is 1.5 divided by 2, which is 0.75. And also note that the average speed of the skier is 1 meters per second. So that means the frequency f is 1/5 or 0.2 moguls per second, right? And we can just substitute these values for a and f into the function mt equals a times sine 2 pi ft, where m represents the height of the mountain of the hill in meters within the mogul as a function of time t in seconds. Therefore, mt equals 0.75 times 2 pi times 0.2, which is a frequency, right? Times t, which can be simplified to mt equals 0.75 sine 0.4 pi t, right? And therefore the height of the skiers through the moguls, ignoring the slope of the hill, is given by this function. mt is 0.75 sine 0.4 pi t, or approximately mt equals 0.75 sine 1.26 t. Okay, this is the height of the skiers through the moguls, ignoring the slope of the hill. And if we consider all of the both of the effect, the height of the skiers through the moguls and the slope of the hill, to describe the skier's actual path of height versus time, we can then just add these two functions. So pt equals ht plus mt, which is minus t plus 100 plus 0.75 sine 1.26 t, okay? And we can sketch this graph also using the online tools or a graphing calculator. So here, I'm gonna show you graph using a online equation solver. Okay, this time we want to plot the combined function which is, remember that the combined function is minus t plus 100 plus 0.75 sine 1.26t, right? But this time, note that the t is equal to or greater than 0 and less than or equal to 100, right? So we only want to plot t between 0 and 100. So let's check the graph. Okay, the command is not correct, so let's check what's wrong. All right, so as you can see here, if we plot this function for t between 0 and 100 inclusive, this function will look like this, right? This is a combined effect of the slope of the hill and the theories of Moguls, which is also shown here, okay? All right, so please have a look at the solutions of this problem. Let me know if you have any questions. All right, if not, let's make a summary of what we have learned for today. So after today's lesson, you should be able to understand that a variety of the real world situations can be modeled using the combined function, right? And then now you should also be able to develop a model to solve real world problems that involve combined functions. All right, so the rest of the time is for you to complete and submit today's homework, okay?